Welcome to our quantum deep dive.
Great to be dagging in.
Today, we're looking at Peter Shor and his, really revolutionary quantum factoring algorithm. We're drawing heavily on a great essay by Yorgo Schneeppert.
Yeah, Schneeppert's piece does a fantastic job setting this up. And to really get Shor's impact, you have to remember where we came from, right? Classical computing.
Bits and bytes, zeros and ones, the foundation of, everything digital until now.
Exactly. Binary. But quantum computing. That's a whole new ballgame. It uses qubits.
Right, qubits. And Schneeppert explains this, they're not just 0 or 1, they can be kind of both at once. That's superposition.
Precisely. Superposition. Think of it like a dimmer switch rather than just on-off. It exists in a combination of states.
Okay, so that allows for a sort of parallel processing, but on a quantum level.
You could say that. It lets the qubit explore many possibilities simultaneously, which is just fundamentally different from a classical bit doing one thing at a time.
And then there's the other really weird part. Entanglement.
Entanglement. Yeah. Spooky action at a distance, as Einstein called it. You link two qubits, and whatever happens to one instantly affects the other, no matter how far apart.
Instantly. That still sounds like science fiction.
It does, but it's real. And it's key. So you combine superposition, exploring many states, with entanglement, linking these states.
Yeah, and you get this, massive potential jump in computing power. For certain problems, anyway.
Exactly. For specific complex calculations, the potential increase isn't just linear, it's exponential. It's a theoretical game changer.
In quantum computing research, as Schneeppert notes, it's still pretty young, relatively speaking.
It is, but there have been these landmark moments, and Peter Shor's algorithm in '94, that was arguably the biggest one early on.
Why? What did it show?
It showed very concretely that a quantum computer could solve a really important problem exponentially faster than any known classical method. The problem: factoring large numbers.
Okay, factoring, like finding the prime numbers that multiply together to make a bigger number.
That's it. And Shor's algorithm, in theory, could factor huge numbers that would take today's best supercomputers, billions of years.
It could do it.
Maybe seconds or minutes, orders of magnitude faster.
Wow, okay. So why should you, listening now, care about factoring big numbers super fast? Seems a bit niche.
But it's not. As Schneeppert's essay really hammers home, the security of so much of our digital world relies on the fact that factoring is incredibly hard for classical computers.
You mean things like online banking, secure emails, passwords?
Exactly. Encryption systems like RSA, they're everywhere. Their security is built on the difficulty of factoring the large numbers used in their keys.
So if Shor's algorithm running on a powerful quantum computer can just breeze through that factoring,
then the locks are broken. The whole foundation of that security crumbles. That's the bombshell Shor dropped. It revealed a fundamental vulnerability.
So understanding Shor, his algorithm, and what it means for, everything from quantum science to cybersecurity. That's really our mission today, drawing on Schneeppert's insights.
That sums it up perfectly. It's a pivotal story.
Okay, let's recap the main takeaways here based on Schneeppert's analysis. Peter Shor's role was absolutely central, wasn't it?
Undeniably. His algorithm was the killer app, the thing that made everyone sit up and say, okay, quantum computers aren't just theoretical toys. They could potentially break modern cryptography.
It showed that for certain problems, like factoring, quantum computers have this almost unbelievable advantage over classical ones.
Right. And the implications for cryptography, specifically things like RSA, which we rely on daily, are just enormous. It exposed a future threat that couldn't be ignored.
Now, Schneeppert also points out, and this is crucial, we're not quite there yet, are we? Building these powerful quantum computers is hard.
Incredibly hard. It's a massive engineering challenge. You need to control these delicate quantum states, these qubits, keep them stable, protect them from noise.
Decoherence, right, where they lose their quantum properties.
Yeah, exactly. And you need error correction. Quantum calculations are inherently prone to errors. So building fault-tolerant machines capable of running Shor on, say, RSA-sized numbers, still a huge hurdle.
So there's tons of research going into just making the hardware work. Better qubits, better error correction.
Absolutely critical work. As Schneeppert highlights, advances there are essential before Shor's algorithm becomes a practical threat rather than a theoretical one.
But the threat is real enough that people are already working on defenses.
Yes, thankfully. This whole situation has spurred the development of post-quantum cryptography, or PQC.
New encryption methods designed from the ground up to resist attacks from both classical and quantum computers.
Precisely. It's a race, in a way. Develop and deploy PQC before large-scale, fault-tolerant quantum computers become a reality. We need our data to be safe in that future.
And SNEPAD ends on a really thoughtful note, kind of stepping back to look at the bigger picture.
Yeah, the ethical dimension. This incredible power, it brings responsibilities.
The potential for breakthroughs in medicine, material science, AI, it's immense. But so are the risks if the power, like code breaking, is misused.
It really forces us to think about how we develop and deploy such transformative technology. There's an ethical responsibility on the scientific community, on policymakers, on all of us, really.
Opportunities and risks, hand in hand, requires careful thought.
Definitely. We need to be proactive about considering the societal impact, security, privacy, all of it.
A really important point to end on. And again, our thanks to Yurgo Shnepat, whose essay provided such a clear and insightful basis for this deep dive.
Absolutely, a great piece laying out Shor's impact.